This is the video covering Mazur's chapter 10. The file is phys0008 slides10.pdf in the usual files area on the web page. So we said earlier in the course that things we wanted to understand before we could study architectural structures, according to Professor Farley, were forces. Okay, check. So we just got through forces, although we're going to continue to use forces all throughout the rest of the term. Vectors, so that's what we're doing now as we move from one dimension into two dimensions. And torques, which will be the topic of chapter 12. Now the next few chapters, chapters 10, 11, 12 of the textbook, are the most difficult material in the course, so we're going to slow down for these chapters. And then once we get through these difficult chapters, the real fun begins. Okay, so we can apply our knowledge of forces from chapter 8, vectors from chapter 10, and torque from chapter 12 to studying some examples of architectural structures. I have an astonishing 86 slides of material for chapter 10, so I expect we will split chapter 10 into two parts, two videos. Here's an old chapter 10 reading question. Can an object be accelerated without changing its kinetic energy? And the answer is yes. So you can change an object's direction without changing its speed, so its velocity can change without changing its kinetic energy. Remember, the kinetic energy is 1/2 mv squared, so that depends only on the speed. So for example, this is really the topic of chapter 11, but once we are in two dimensions, I can make an object go around and around in a circle, and then it is moving at constant speed, or actually it may be almost, not quite constant speed. In this case, if I do it this way, you can't see what's going on, but this really is constant speed. This is approximately constant speed. And you can see that even though the speed is not changing, the velocity is changing because the direction of the velocity vector is changing. Okay, so that you can do that in more than one dimension. You can do that infinitesimally, instantaneously. And then in a single dimension, it's hard to do that instantaneously, but over a finite interval, you can go from moving this way to moving this way. So in that case, you can change the object's velocity. In other words, you can accelerate the object without changing its kinetic energy. So remember, acceleration is change in velocity, and velocity is a vector. So if you change not only the magnitude, the speed, but if you change the direction of the velocity vector, that counts as acceleration. So bear that in mind. One thing we're going to get used to right away now in chapter 10 is we'll use two different variables, x and y, instead of just using x for everything. So our new convention is that most of the time the x-axis will point to the right, and most of the time the y-axis will point up. Although there's some special cases where we'll want to use a more convenient rotation. For example, if we're going downhill, usually we'll make one variable point downhill. To get used to using y as the vertical coordinate and x as the horizontal coordinate, we're going to use the ball popper. We're going to return to the demonstration of the ball popper, and what we're going to do is to combine our familiar constant acceleration example of, for example, throwing or dropping a ball, okay, but except instead of in the x coordinate, it'll be in the y coordinate. So we'll say a sub y is constant. In fact, it'll be minus g. Then we'll do v sub x. So we have constant acceleration in the y direction, and we'll have constant velocity in the x direction. And let's see what happens when we combine those. And I guess we can even start to work out what will happen when we combine those. For constant acceleration, for example, we have y is y initial plus v y initial t plus 1/2 a sub y t squared, and we're going to have a sub y equal to minus g. So then we can replace a sub y with minus g, and this then becomes minus 1/2 gt squared. If we wanted to, we could take the derivative of this equation, and we could get dy by dt. This is a constant, so there's 0 plus, this cancels 1 power of t, this is vy initial, and then we have the 2 cancels the 1/2, and we have minus gt. So, and this, by the way, is v sub y. So v sub y is v sub y initial minus gt. Okay, that's kind of familiar from our constant acceleration results, except we're writing y instead of x. And then, meanwhile, the x coordinate will just be x equals x initial plus v sub x initial t. Okay, and then v sub x is just our constant, v sub x initial. Once we have those two equations, actually one thing that it's often useful to do is to take this equation and solve it for the time. And also we can say, let's let x initial equal 0, and then we'll solve for time. So we have x equals vx initial times time. So that gives us that the time is x over vx initial. Okay, so you let x initial be 0 and then solve for t. And that gives us this value for the time. So then we can essentially write y versus x instead of writing y versus t. We can then plug this value for time into this expression for y versus time, and we'll get y versus x. So we have y is y initial plus vy initial times x over vx initial, and then minus 1/2 g, and then here's x over vx initial, the quantity squared. And we can rewrite this so that it's a little more obvious where the x and x squareds appear. So we can say y is y initial plus vy initial divided by vx initial times x, and then minus g over 2vx initial squared times x squared. So this is like a coefficient in front of x squared. And you may or may not recognize this result as an equation for a parabola. So it's that y is a quadratic function of x. So actually, if you graph y as a function of x, you'll get something that sort of looks like this. Okay, so how do we get that? We combined constant acceleration, which is a kind of familiar result from chapter 3, except we're doing it now in the y variable instead of the x variable, with constant velocity in the x coordinate. And how did we achieve that? So in the ball popper demonstration, we're going to take the motion of just tossing a ball up and down. So we have a little mechanical device that will toss a ball up and catch it when it comes back down. And we're going to then just take that little mechanical device that throws the ball up and catches it, and we're then going to make it do so while it is rolling at constant horizontal velocity. So that combines those two motions of constant acceleration under the influence of gravity in the vertical coordinate with constant velocity in the horizontal coordinate. So here is our old friend, the ball popper. So there is a ball in here in a little spring-loaded contraption, and when the spring-loaded contraption comes over to this point, it will throw the ball up in the air. Initially, let me just hold it in place. So the horizontal velocity will be 0. I'll just move the ball popper over here so you can see the vertical motion all by itself. Okay. So that's familiar from chapter 3, but now let's superimpose on that free fall only along the vertical axis. Let's superimpose on that the separate motion of the cart moving at constant horizontal velocity. So the motion is constant velocity in the x-coordinate and constant downward acceleration in the y-coordinate. So let's see what that looks like when we combine the two parts together. So let's draw the velocity vector at the instant the ball is launched from the cart and then decompose it into vertical and horizontal components. So at the instant the ball is launched from the cart, the velocity vector points in this direction, so it's tangent to the motion at this point of the launch. So we can take that vector, I'll redraw a bigger copy of it, and then we can decompose it into a horizontal portion and a vertical portion. The textbook sometimes calls this v initial y component with an arrow over it and v initial x component with an arrow over it. This is a little bit of unusual notation. But then if you take this vector and you make a copy of it over here so that you're putting the two parts head to tail, you can see that they add up to the original vector. So you can say that vi x component plus vi y component is this original initial velocity vector. Okay, so once again, when you decompose it in this way, you can take the x part and then you can take a copy of the y part, and when you add them together, the way you add vectors together is to put them tip to tail, then the result that you get is the original vector. Okay, so here's the horizontal component, and then this was the vertical component as originally decomposed, but we can make a copy of it over here. It's the same vector. If we move it over, it still has the same magnitude and same direction. So then the way we add two vectors is we place them tip to tail, and then the result is that the two components that we've decomposed the vector into add back up to the original vector. And decomposing vectors into two perpendicular components is something we will do again and again. It'll be a really useful thing to do later with forces. Okay, remember in the video clip, the ball leaves the ball popper and then flies up and then comes back down and is caught by the ball popper. So the ball is horizontally moving from left to right, and then vertically it's undergoing motion at constant acceleration. Which one of these 7 graphs best represents the acceleration vector in magenta and the velocity vector in yellow the instant after the ball is launched from the cart? Let's look at our possibilities. So we could have an acceleration downward, an acceleration upward, an acceleration downward, acceleration downward, acceleration downward, 0 acceleration, acceleration downward, and then velocity up and to the right, or velocity just to the right, or velocity down and to the right, or velocity 0, or velocity straight down. Which one of these do you like? I think the instant immediately after the ball is launched from the cart, its velocity vector points up and to the right, and its acceleration vector is just that due to gravity. So I think its acceleration vector should point straight down due to gravity. The only force acting on it is gravity. It's the instant after it's released from the cart. But its velocity vector has a component to the right and a component up. So I think I like answer A, alpha. What about at the very top of the ball's trajectory? So when the ball is up here, what is its velocity vector and what is its acceleration vector? So you can pause and think for a moment. To get its acceleration vector, you could look at the change in its velocity vector, or you could just imagine the forces acting on it. So I think there is still only one force acting on it, which points downward. So I think the acceleration still points straight downward, and I think the velocity vector points directly to the right. So you can see an instant earlier, the velocity vector was a little bit up and to the right. An instant later, the velocity vector is a little bit down and to the right. At that instant, the velocity vector is straight to the right. And also, to change it from going a little bit up and to the right to be going a little bit down and to the right, well, that's a change in the downward direction, you see? So it was like this way, and then it's like this way. And the way you turn this vector into this vector is you add something that points straight down. So I think that makes sense, too. Let me just say that last point again. The velocity vector, the instant before it reached its apex, was pointing up and to the right. I'm exaggerating how up it was, but it's up and to the right. and then you want to turn it into something that points down and to the right. And if you add something that points straight down to something that is pointing up and to the right, the result, when you combine these arrows tip to tail, is something that points down and to the right. I guess if you want to do it in a slightly less exaggerated way, you could say that's up and to the right. And what we want to get is something that an instant later, or a little bit later, is down and to the right. And what you have to add to this orange arrow to get this blue arrow is something which points straight down. So I think that makes sense. So the acceleration, to go from this velocity a little bit before apex to this velocity a little bit after apex, what we add to the velocity is something proportional to the acceleration, and that is directly down. Which graph best represents the acceleration vector in magenta and the velocity vector in yellow the instant before the ball lands back into the cart? Well, the instant before the ball lands back into the cart, its velocity vector is tangent to this line, so I think it points down and to the right. And then after it lands in the cart is acting on the ball, but before it lands in the cart, there's still only one force acting on the ball, and that's gravity. So I think the instant before it lands in the cart, its acceleration vector still points directly downward. And I think that is consistent with answer D here. So I think I like D, delta, for the instant just before it lands in the cart. And remember, we liked A, alpha, for the instant just after it was launched from the cart. And then at the instant when it was at its apex, I don't think we circled a result, so I think I like answer Charlie, C, for the instant when it is at the apex of its trajectory. So in all three cases, the acceleration is downward with magnitude little g, because the only force acting is gravity. But just after launch, the velocity is up and to the right. At the apex, the velocity is to the right with no up or down component. And just before being caught, the velocity is down and to the right. Which of these three paths best represents the trajectory of a cantaloupe thrown horizontally off a bridge? Okay, so I guess I'll take my cantaloupe and I'll throw it perfectly horizontally off a bridge. So if I look at the blue or white curve here, what I don't like about it is that the tangent vector, when it's first released, seems to point a little bit downward. And we'll see a zoom into that in a moment. This one, the tangent vector initially is horizontal, so I think I like that. The magenta one, the tangent vector also initially is horizontal, but this looks like the kind of old-fashioned like Roadrunner cartoon, where the coyote goes off the cliff and then doesn't realize for a moment that he's gone off the cliff. And that doesn't really seem like good physics, because once the cantaloupe is released, it should be accelerating downward, which means that you should have a kind of downward curvature, right? So it should be a concave down curve, not just a flat line if it's accelerating downward. And in fact, if we zoom in on the top left corner, the launch position, you can see that the yellow curve starts out with a tangent line, which is horizontal, and then it gently curves downward, which I think we expect for constant acceleration. Constant acceleration means constant downward curvature. That actually means constant downward second derivative of the curve. The magenta line just seems to be flat, so that doesn't seem consistent with a constant downward acceleration. And then this white or blue line looks as if even from the very outset it has a downward slope, which would make sense if the ball or the cantaloupe were thrown downward like this. But if you're throwing the cantaloupe horizontally, then its tangent line initially should be horizontal, because initially it has a non-zero horizontal component of velocity, but initially its vertical component of velocity should be 0. 2 steel balls are released simultaneously from the same height above the ground. We said steel balls because we want to say that air resistance is negligible, because the presence of air resistance actually would affect the answer to this question. So we're going to say in the absence of air resistance. So one ball is simply dropped, okay? So it has 0 initial velocity. It's not thrown downward, it's simply dropped. And the other ball is thrown horizontally. So it's thrown in such a way that it has an initial component of velocity in the horizontal direction, in the x direction, but it does not have any initial component of velocity in the y direction. That component would be 0. And the question is, which ball will hit the ground first? So if you think about this, in the absence of air resistance, this ball has just a single force acting on it from the instant after it's released until the instant before it hits the ground, and that force is the gravitational attraction by Earth. And if you think about this ball, in the absence of air resistance, from the instant after it's released until the instant before it hits the ground, it also has just a single force acting on it, which is the downward force that Earth exerts on it, the gravitational force. So in both cases, you say y equals y initial, and then there's 0 initial velocity in, well, I'll write the term and then we'll cross it out. Y initial plus v sub y initial times time, but v sub y initial is 0, and then minus 1/2 gt squared. And in the other case, we have y equals y initial plus v sub y initial times time, but we said v sub y initial was 0, minus 1/2 gt squared. So you say, well, what time is it when we reach y equals 0? and it's the same time. 0 equals y initial minus 1/2 gt squared gives us t when it hits the ground. T when it hits the ground is just the square root of 2 times y initial divided by little g. So it appears that in the absence of air resistance, the horizontal motion makes no difference at all to what time will hit the ground. By the way, if you want, so I think our answer is C. Charlie, both balls hit the ground at the same time. By the way, if you want a little brief, very tiny digression that is not in our textbook, if we did account for air resistance, then the air resistance would be a drag force which opposes, it goes in the opposite direction of the ball's velocity vector at a given instant, and it would be proportional to the square of the speed at which the ball is going. So I think in that case, air resistance would slow down the ball that's moving at higher speed more than it would slow down the ball that's moving at a less high speed. And since there is a horizontal component here, then the overall speed, and this drag force is proportional to the square of that overall speed, is bigger for the ball which is thrown with a horizontal component. So you don't need to know this, but I do think that if you did really account for air resistance, then the ball which is thrown with a significant horizontal velocity initially would hit the ground a little bit later. But in the absence of air resistance, the two balls hit the ground at the same time. Okay, it's time now to tell a story that appears in every introductory physics course, which is there is a monkey who just happened to be easily frightened by loud noises, and the monkey is minding his own business, clinging to a tree branch with one hand, and with the other hand, the monkey is enjoying some bananas he stored away. And then while the monkey is minding his own business, off in the distance comes an ecologist wearing a safari hat, and the ecologist doesn't want to hurt the monkey. The ecologist wants to collect a DNA sample for the primate genome project. And in order to collect this DNA sample, the ecologist is going to shoot a dart gun, which is not going to hurt the monkey in any way. It will just tranquilize the monkey for the collection of this DNA sample. However, it does turn out that this dart gun makes a loud noise, and the loud noise is going to frighten the monkey, and the instant that the monkey hears the loud noise, he's going to be a little bit scared and will let go of the tree branch and will start to fall from the tree. Now I need to pause for a moment to ask you a question of tremendous practical importance. Should we leave the story intact so that the ecologist shoots the dart gun, which just contains a harmless tranquilizer, at the monkey, whom we might nickname Nim Chimpsky? Or should the ecologist instead collect a harmless DNA sample from the old Saturday Night Live cartoon character Mr. Bill? And I can add that collecting a DNA sample from Nim Chimpsky while he's out eating bananas in the tree might explain why he was smart enough to learn all those words of American Sign Language, if you saw the movie. Or, if we tranquilize Mr. Bill, if we actually manage to find any real DNA in the sample from Mr. Bill, the result will definitely be a publishable paper, if not a Nobel Prize. In past years, I always ask people to vote. Do we want to study Nim Chimpsky, or do we want to study Mr. Bill? But this year, I get to choose, so I am going to tranquilize Mr. Bill. So I guess we decided we're going to shoot the tranquilizer pellet at Mr. Bill. So here's some things you need to know about the way this demonstration works. It takes the pellet some time to travel across the width of the room. If you look closely in the photo you're looking at, there's a little copper tube which represents a pellet gun, and it's actuated by my blowing a little puff of air into the tube, and that propels a little steel ball to fly across the room. And the question is, should I aim it directly at Mr. Bill, or should I aim it a little high or a little low? Because gravity will cause Mr. Bill to fall a little bit by the time the pellet reaches his position, maybe we need to aim low so that the pellet is low enough to hit him by the time the pellet gets there. Or maybe because the pellet takes a parabolic arc rather than just traveling directly in a straight line, maybe we actually need to aim high to account for the fact that the pellet will drop a little bit in this parabolic arc by the time it gets there. In fact, I would say if we wanted to hit Mr. Bill and Mr. Bill were not going to let go of his tree branch, then I think we would have to aim a little bit high to account for this parabolic arc. So I guess if Mr. Bill were not frightened by the noise of the pellet being released and did not immediately let go of his tree branch, I guess we would need to aim high so that the parabolic curve would be accounted for in our calculation. So here is the scenario. Initially, Mr. Bill is up here hanging onto a tree branch with his hands. And I am down here with the dart gun. I'm the ecologist. Then I want to aim the dart gun some angle theta above the horizontal. So in this case, let's suppose I choose the angle theta so that a line pointing straight along the axis of the dart gun points directly toward Mr. Bill where he is hanging on to the tree branch. So the initial velocity of the dart will be along this direction. So when we first release the dart, the initial will have a horizontal component like this and a vertical component like this, so we can decompose it into the two components, and its initial velocity will be just right along the axis of that dart gun. So then, if we aim directly at Mr. Bill, the question is, well, will the effect then be spoiled by the fact that, of course, the dart will take this parabolic path that we just worked out a few slides ago rather than a straight line path? And I claim that if Mr. Bill were indeed going to stay put where he is throughout the whole time and not be frightened by the sound of the dart gun, I think we would indeed miss Mr. Bill, because indeed this parabolic drop of the pellet to form a parabolic arc would cause the pellet to land too low. But at the very instant that the dart is released from the dart gun, Mr. Bill is frightened by the sound of the release of the dart from the dart gun, and he lets go of the tree branch with his hands, and he begins to fall down at an acceleration g. And in fact, Mr. Bill is falling downward with a downward acceleration of magnitude g, and the dart is also accelerating downward with a downward acceleration of magnitude g. And so the question is, well, will gravity affect the dart and affect Mr. Bill in equivalent enough ways such that by the time the dart crosses the path of Mr. Bill, they will actually be at the same altitude, and therefore the dart will strike Mr. Bill, thereby tranquilizing him and allowing me to collect safely a DNA sample from Mr. Bill. So what shall I aim for? Well, maybe I should aim high, because the steel pellet is so much more massive and so much heavier than Mr. Bill that it will be pulled down more by gravity. Maybe I should aim low, because Mr. Bill will be falling while the pellet travels. Well, Mr. Bill will indeed be falling while the pellet travels, but maybe the pellet will also be falling while it travels. Aim directly for Mr. Bill. This is clearly what you would do if gravity were absent. The presence of gravity will affect Mr. Bill and the pellet in the same way. They both experience the same downward gravitational acceleration. So aiming directly for Mr. Bill will result in a direct hit. Or how much below Mr. Bill you need to aim depends on the speed with which you fire the pellet, because the time that it takes the pellet to reach Mr. Bill will depend on how fast the pellet is shot. I'm not going to give away my own answer yet. So let's try writing equations for the x and y coordinates of Mr. Bill versus time, and the x and y coordinates of the pellet versus time in terms of the initial position of Mr. Bill, shown on the diagram, and the angle at which the pellet is released, and the initial speed at which the pellet is released. So let's call this position 0, 0, x equals 0, y equals 0, and then we're going to call the initial position of Mr. Bill x initial, comma, y initial. Then we're going to say x of Mr. Bill as a function of time is just x initial, because Mr. Bill moves only downward. He just drops from holding on to the tree. He does not move horizontally at all. And then we can say y of Mr. Bill versus time is y initial, and then minus 1/2 gt squared, because he just releases his grasp on the tree. He's not pushing himself vertically. So he starts with 0 initial speed, but he lets go of the tree at time 0. Time 0 will be the same as the time that the pellet is released, because Mr. Bill is frightened when he notices the release of the pellet, and that causes him to lose his grasp on the tree. Meanwhile, x of the pellet versus time is vx initial times t. Okay, so the pellet has some initial velocity, vx initial, and then the pellet also has some vertical velocity, vy initial. See, this is vx initial t plus 0, because at time 0, the pellet is at x equals 0, y equals 0. So this is y equals 0, and this is x equals 0, and this point is 0, 0. Then we have y pellet as a function of time. So we start at y equals 0, but we have vy initial t, and then minus 1/2 gt squared. Then let's do a little bit of trigonometry. Here is v initial, and here is the angle theta with respect to the horizontal at which we release the pellet. So we notice that this is also vy initial. So we can say vy initial divided by v initial is opposite over hypotenuse. So that is sine theta. And we can say that vx initial divided by v initial is adjacent over hypotenuse. So that is cosine. So then we can write that y initial is v initial, it's just initial speed, sine theta, and we can say vx initial is v initial cosine theta. Okay, so this v initial is just the speed, which will depend on how hard I blow into the little tube that propels the pellet. Then notice that if I aim directly at Mr. Bill, then using this very same angle theta, then y initial over x initial is opposite over adjacent, because this also equals x initial, and that equals the tangent of this same angle theta. If I aim directly at Mr. Bill, then tan theta equals y initial of Mr. Bill divided by x initial of Mr. Bill. So let's review our assumptions. Mr. Bill starts from rest at x initial, y initial, and he drops straight down. The pellet starts at x equals 0, y equals 0. And let's say I am going to aim directly toward Mr. Bill. The pellet starts with some initial speed, v initial. There's going to be some angle with respect to the horizontal when I take that initial speed and turn it into an initial velocity with x component and y component. And if I aim directly at Mr. Bill, we will find that the y component of the pellet's initial velocity is v initial sine theta. Here's the angle theta. The x component of the pellet's initial velocity is v initial cosine theta. And it's that same angle theta that relates x initial of Mr. Bill and the y initial of Mr. Bill. Because if we take this initial position of Mr. Bill, we say, okay, it has a y component, that's how tall it is, and it has an x component, that's how far over it is from 0, 0. Then you can say, okay, opposite over adjacent is the tangent of theta. So we wrote that down over here. Tan theta is y initial divided by x initial of Mr. Bill. Then that same angle theta, if I'm aiming directly at Mr. Bill, represents how we decompose the initial velocity of the pellet into horizontal and vertical components. So we have Vx initial like this, Vx initial, and we have Vy initial like this. Or you could draw it up here if you want to. If you draw it up here, then you can see that Vx initial, if you draw it as a vector, plus Vy initial, if you draw it as a vector, adds up to V initial if you draw it as a vector. So here's Vy initial. And we're going to say that at time 0, okay, so it's important to say what happens at time 0. At time t equals 0, I blow into the dart gun, which releases the pellet in this direction, in the, with some initial speed V, which we don't know, but I can control by how hard I breathe into the pellet gun. And the angle of inclination of that initial velocity of the pellet with respect to horizontal is theta. And it's that same angle theta from where I'm standing over to Mr. Bill's initial position with respect to me, where he's holding on to the tree before letting go. And then at that same time t equals 0 that the pellet is released from the dart gun, Mr. Bill is going to let go of the tree he's holding onto. And you could say, why is that true? Well, in the story, it's because Mr. Bill is frightened by the actuation of the pellet gun and he loses his grip on the branch. In real life, it's because there's a little electric circuit that causes the little electromagnet that is holding Mr. Bill onto the stand he's holding onto to disengage. So at the very instant when the pellet comes out of the pellet gun, a little electrical contact is unplugged, and that little electrical contact being unplugged causes the electromagnet to turn off, which then causes Mr. Bill to let go of the little stand that he's holding onto and to fall directly downward. So we know Mr. Bill will have a constant x value, x equals x initial, but his y value will follow y initial minus 1/2 gt squared. We know that the pellet will follow the parabolic arc of projectile motion, and that is described by x of the pellet is vx initial times time, y of the pellet is vy initial times time minus 1/2 gt squared. And then we can plug in what we know about this angle theta, which is indicating that we're aiming at Mr. Bill. And we want to ask, will the pellet hit Mr. Bill? And one way to ask that question is we have this line, x equals x initial of Mr. Bill, which is the x coordinate Mr. Bill stays at. And at the instant when the pellet reaches that value of x, how different are the pellet's value of y and Mr. Bill's value of y? So let's see if we can figure that out. So this x pellet of t is v initial cosine theta times time. And this y pellet of t is v initial sine theta times time minus 1/2 gt squared. And let's ask, at what time t does x pellet equal x bill? In other words, at what time t does the path of the pellet cross the downward path of Bill? So we can just write that down. So say our expression for x pellet equals our expression for x bill. V initial cosine theta times t equals x initial of Mr. Bill. And that gives us t equals x initial divided by v initial cosine theta. Then let's ask, at that time t where the pellet's path crosses Mr. Bill's path, how do the vertical coordinate of Mr. Bill and the vertical coordinate of the pellet compare with one another? So let's try subtracting y bill and y pellet, and if the difference is 0, then we'll say they're at the same place. So y bill minus y pellet equals y initial minus 1/2 gt squared minus v initial sine theta t minus 1/2 gt squared. And the minus 1/2 gt squared is the same in the two terms, so it just cancels out. And then we get equals y initial minus v initial sine theta t, which is y initial minus v initial sine theta. And what's our expression for t? It is x initial divided by v initial cosine theta. It seems like the v initial cancels out, and we get y initial minus x initial tan theta. And notice that tan theta equals y initial over x initial. So you see that's y initial minus x initial, y initial over x initial. So then the x initial cancels out and we get 0. So y bill equals y pellet at the instant when x bill equals x pellet. So at that instant when the pellet crosses the downward path of Mr. Bill, they actually are at the exact same vertical location. So I claim that it doesn't matter whether I fire the dart at a relatively low speed or a relatively high speed, as long as I shoot the dart at a high enough speed that it crosses this line before it hits the ground. In other words, if I shoot it so slowly that it doesn't make it that far, it just comes here, then we're not going to get a collision, because the collision, if it happened, would happen down beneath the level of the floor. So that doesn't make sense. The equations don't know that the floor is there. But as long as I shoot it with a high enough speed that it makes it past this line of Mr. Bill's travel before hitting the floor, then I claim we will have a direct hit between the pellet and Mr. Bill, as long as Mr. Bill lets go of his tree branch at the same time as I fire the pellet through the air. So let's see if it works out that way in the video clip. Let's just say I'm a clever ecologist and I know that at the instant that I shoot the dart gun at the monkey, he is going to be scared and he's going to let go of the tree branch and fall down. Actually, I'll show you what that looks like all by itself. So it turns out we have a little trick here. The way we arrange for this to happen is, there's actually a little electromagnet up here in the tree branch. And the little electromagnet creates a magnetic field which attracts this little steel tip which is screwed into the monkey's head. And so you can see there's no attraction right now, but when the electromagnet is energized, the electromagnet is holding the monkey in place. And then the very instant when our tranquilizer dart ball passes by the end of this copper tube, it will flip this little switch which then deactivates the electromagnet. So the electromagnet lets go of the monkey at the very instant when the tranquilizer dart leaves this tube. And then of course the monkey, once he lets go of the branch, once the magnet lets go of him, but you say once he lets go of the branch, he'll be in free fall, so then he will fall directly down under the influence of Earth's gravity. I don't see Mr. Bill over there. Oh, there we go, I see Mr. Bill over there. Okay, I found him. I need to aim. If we aimed the pellet initially to point directly toward Mr. Bill, then that minus 1/2 GT squared term for the pellet will match that minus 1/2 GT squared term for Mr. Bill, and by the time the pellet reaches this x value, they will be at the same y coordinate. So they should intercept one another, and that's true no matter what speed I use to launch the pellet, as long as I use a sufficiently high speed that the pellet actually reaches this x coordinate before it hits the ground. Then notice that the axis of the tube extrapolates directly at Mr. Bill. Let's see what happens. Whoa! I think that was a direct hit. Let me try the same thing, but I'm going to blow less hard. So hard enough that it does, cross the room, but I'm going to try to impart a smaller initial speed to the pellet. And again, I'm still aimed directly for Mr. Bill. All right, let's try it one more time. This demonstration normally happens on the Wednesday just before fall break. Okay, so let's try, I guess there's a certain amount of randomness in how hard I blow each time. So the initial speed will vary, but the initial angle is always such that the pellet is heading directly toward Mr. Bill's initial position. I'm going to do a couple more rounds. I'll try to vary a little bit the speed at which how hard I blow. So I'll vary a little bit the initial speed, but I'm still aimed directly at him. And then we'll focus in on Mr. Bill, so you can see that the thing that varies as I change how hard I blow is simply the altitude at which the pellet and Mr. Bill intersect. So by the way, when we said aim directly for Mr. Bill, this is what you would do if gravity were absent, and the presence of gravity will affect Mr. Bill and the pellet in the same way. Therefore, aiming directly for Mr. Bill will result in a direct hit. You can see directly how that works out because this 1/2 gt squared term is the same for the vertical position of Bill, Mr. Bill, and the vertical position of the pellet, and that does indeed just cancel out because gravity affects the vertical motion of Mr. Bill and the vertical motion of the pellet in the same way. So then we really are left with the same result we would get if there were no gravity, if g were 0, and if we just aimed directly at Mr. Bill and went in a straight line. Oh no, it is a direct hit on Mr. Bill. From a height h above the ground, I throw a ball with an initial velocity that is non-zero only in the horizontal direction. Vx initial is bigger than 0, but Vy initial equals 0. How do I determine how long it takes to reach the ground? So you can look at these options, and let's see if we can figure that out. So I guess we have constant velocity in the horizontal coordinate. X final is x initial plus Vx initial t. That's not telling us anything about the vertical motion. And meanwhile, we have y final is y initial plus Vy initial t plus 1/2 a sub y t squared, and constant acceleration means we have a sub x is 0 because there are no forces in the horizontal direction in the absence of air resistance, and we have a sub y is minus g. Let's say y final is 0 because the ground is at y equals 0, so we'll say 0, which is the height of the ground. Y initial is h, and then we said v sub y is 0, and then we said a sub y is minus g, so that's minus 1/2 gt squared. So h minus 1/2 gt squared equals 0. In other words, y final is 0, y initial is h, and then we have this 1/2 at squared term, and the acceleration is minus g. So there's minus 1/2 gt squared indicates its fall under the constant force of Earth's gravity. So I think I like answer D, delta. From a height h above the ground, I throw a ball with an initial velocity that is non-zero only in the horizontal direction. Vx initial bigger than 0, Vy initial equals 0. If the ball's initial x-coordinate is x initial equals 0, how do I determine the x-coordinate where the ball hits the ground? Well, first we figure out the time when the ball hits the ground, and the time when the ball hits the ground is determined by the vertical motion. So we wrote this equation down on the previous page. So if we start from a height h and we fall down and we had 0 initial velocity in the y direction, then we can solve this for time, and we get time equals 2 times height divided by little g, the square root of all that. Then you want to know the x-coordinate where it hits the ground. We just plug in that same value of time here. So I guess we have x final is Vx initial times that time, which is just square root of 2 times height over little g. X final is x initial plus Vx initial times time, with time given on the previous page. I think I like answer C, Charlie, for this. Exact same scenario. From a height h above the ground, I throw a ball with an initial velocity that is non-zero only in the horizontal direction. How do I determine the x and y components of the ball's velocity, v sub x and v sub y, the instant before the ball hits the ground? Well, I know what time the ball hits the ground, so I need to figure out v sub x and v sub y at that time. In the x direction, we have constant velocity. V sub x just equals v sub x initial. And in the y direction, we have constant acceleration. So v sub y is v sub y initial minus gt. This is a special case of v sub y is v sub y initial plus a sub y times t for constant acceleration, but we have acceleration in the y direction is minus g. We just simply plug this time into this result, and that gives us the x and y components of the object's velocity just the instant before it hits the ground. The archer fish, shown in the figure, peering from just below the surface of the water, spits a drop of water at the grasshopper and knocks it into the water. People often point out the kind of interesting scenarios in our worksheet problems, so I hope you enjoy this interesting scenario. The grasshopper's initial position is y initial vertically and x initial horizontally. And if the launch angle of the drop of water is theta with respect to the horizontal, how fast is the drop moving when it leaves the fish's mouth? In other words, how fast does the fish have to spit a drop of water in order to hit the target? So you can maybe imagine that if the fish spits the drop of water at an extremely high speed, then the path won't really have too much time to curve, whereas if it spits the drop of water at a relatively low speed, then it will have plenty of time to kind of arc into a parabolic shape. In fact, you can kind of imagine if it's a really low speed, then the droplet of water will kind of just curve down like this. So for some fixed angle at which the fish spits the droplet of water, there's going to be some relationship between how fast the fish spits the water and how much it has time to bend into an arc. So, and you can probably know this from your experience with spraying a garden hose. So if it's at relatively low speed, there will be plenty of time for it to bend into a parabolic arc, and if it's at a very, very high speed, then it'll travel this horizontal distance before it has much time to curve downward. So our scenario is this is x equals 0, y equals 0. So x initial is 0, y initial is 0. X final is some given value, y final is some given value where the grasshopper is. So it's y final is how far up the drop of water has to go to hit the grasshopper. X final is basically how far over the drop of water has to go to hit the grasshopper. I mean, I guess the fish could control both the angle and the speed, but let's say that the angle is fixed and the fish is just controlling the speed. So let's try to figure out what speed is necessary for the drop of water to hit the grasshopper so that the fish gets his meal. So we have the standard equations for projectile motion. That means constant velocity in the x direction. So we have x final is x initial plus vx initial times time, except that we said that x initial was 0. We have y final is y initial plus vy initial times time plus 1/2 a sub y t squared, but we know that a sub y is minus g, so we can replace this with minus 1/2 gt squared. We also said that y initial was 0. In this case, it's convenient for us to say vx initial is v initial cosine theta and vy initial is v initial sine theta. And the way we get that is we can say here is v initial and we can split it up into components. So this is vy initial and this is vx initial. So this is also vx initial and this is theta. Sine theta is opposite over hypotenuse, so that's vy initial over v initial. Cosine theta is adjacent over hypotenuse, so that's vx initial over v initial. So then that gives us vy initial is v initial sine theta and vx initial is v initial cosine theta. So let's substitute and we get x final equals v initial cosine theta times time, and we can solve that for time. So the time at which the water droplet crosses the horizontal coordinate of the grasshopper is x final divided by v initial cosine theta. Then we substitute for y final, we get, so vy initial is vi sine theta, and then here's time minus 1/2 gt squared. Then we can plug in this value of the time. Actually, everything in this problem is given except for v initial. And of course, you have numbers rather than symbols, but you can take this equation and just solve it for v initial in terms of a bunch of constants. And it looks like kind of a gross expression, but it's just a bunch of numbers. So this is the square of v initial. So I guess if you took the square root of this whole thing, you would get some value for the required initial speed.